my understanding of your story is that what we look at and we see is that in the past, what we know for sure is that we were in this sort of medium, this plateau you've written there. But what picks out that medium level is maybe not so clear. And then the thing you want to appeal to is that you say there's a special point. And the special point is the vacuum, or I guess the vacuum state, right? And so it's if you have some sort of story that takes you from the point to this medium entropy, then we're okay with that tuning.
So I feel that what you just said about this philosophical thing, that you have an elegant statement at the beginning, then you're okay. I feel, strictly speaking, that that's in conflict with the intuition people tend to use if they want to get worried about tuning. I think there's tension there. It's different kinds of philosophies you're applying. I personally just don't know what to expect of cosmology. I think on one hand, the other thing I like to say is that, so one of the things, actually I'm going to...
Well, would you say that there's that tension even classically in a non-expanding universe?
Yeah, I think it's a pretty deep tension, and somehow we've worked ourselves into a state. So I like to describe the state of inflation where there's consumers. So inflation is this industrial strength field of physics where people seriously wear these funny outfits and build amazing satellites and send them out to space and take these amazing, totally stunning data sets which we didn't even know could exist back when I was a graduate student. And then inflation can take a curve and just shoot it through all these wiggles. And so this is this great practical thing. And then, so those are consumers of inflation are just really, so why do what are the priors that make a great theory of cosmology? I've been living this world where I'm stressing about what are we really trying to understand? How do you define tuning? How do we resolve it? The kinds of questions you've raised. Is it an elegant statement of initial conditions? Blah blah blah. Ultimately, it's about what makes cosmologists happy. It's like these guys over here are just happy. They have a narrative. They shoot the inflation curve through the wiggles. If the originators of inflation says it solves tuning problems, well, it must, because look how well it fits the data. Meanwhile, I think you can wrestle with weird multiverse pictures and wonder what tuning really means, and I don't think we have good answers. And the ultimate question is, can wondering about that help the field make progress? So I don't know. I don't think I can't tie that up with a bow. And I think what you described is just a tension between, is a beautiful symmetric statement about the initial conditions, is that going to make us happy enough? Or are we going to turn around and say, wait a second, look how finely tuned that is? I don't know.
Again, if the tension exists even classically,
yeah.
it seems like something for people with philosophy of science can just easily, they're going to make as much progress as they already have, probably. Whereas if it's something novel...
Or maybe less.
Or if it's something novel about cosmology, then it's maybe something where we need to really grapple with the cosmology. And that's what I'm trying to...
So the way I translate that for myself is the worrying about these kind of things will earn their keep if they help me come up with a more exciting physics theory that people actually think is better than what we have. And otherwise it's just spinning our wheels. And I don't know the answer. I don't know if it will pay off in that way. So like any science, you set out in some new direction. But it's hard to let go. It's just hard to let go of these questions, for better or worse. Yeah, Charlie.
Well, I feel that tension too, because when you say that the simple initial condition is its simplicity looks like it's an okay thing to have, but I feel the tension. For me, the tension comes back in the classically in a classical finite model, which I understand best. It comes back in the form of the Boltzmann brain problem, because if you start off with a simple initial condition, then that's okay, but why are we atypically early in the evolution? Because most of the trajectory is is not like the way the world is. So,
So who should tell people what a Boltzmann brain is, me or you?
Well, I was going to do it.
Oh, you'll do it in your talk. Good. So I was going to
Yeah.
wasn't going to dwell on Boltzmann brain in my talk, but we'll get there. So I'm just going to leave it. I think what I'm going to do is go to the other part of my talk and just say the first part of the talk has succeeded because it stirred up these questions. I don't have neat little answers for them. I think it's appropriate for this group to wrestle with them, and I'm glad we're here to do that. And now I'm going to go on to the second. So I put some sort of reminders of Part A in the slides, takeaways. I think we've discussed all of this. They're just now on the record in the slides. And now I want to, we've talked about this idea. Yeah, if we go back to physics as it's practiced in most parts of the physics departments, like you are happy to have the right equations, and you get to choose whatever initial conditions match the physical problem you're working on, then we're done. Cosmology is in great shape. We have great equations, well, general relativity and all the particles, and throw in some dark matter and some dark energy, and you get a beautiful picture of the universe with all kinds of consistency checks, and you're in great shape, with or without inflation, and without worrying about tuning problems. So well, I put a humble version here because there's also this funny phenomenon where cosmologists can get into heated arguments about whose initial state of the universe is the best, and they argue about whose Wick rotation best matches something they do in particle physics or whatever. And I find those absolutely ridiculous arguments because I don't know why nature would listen to these pompous cosmologists arguing about their favorite initial state. But a more humble version, which is just choose some initial state that works, I think is we're done. Okay, but I want to go on to part, and the fitting the data is a big deal, so I have these pretty things. So now what I want to do is completely, so I've been talking about the biggest possible picture, the universe and the meta-universe and all these big questions, and now I want to zoom my focus way down to this tiny little toy model and focus on this tiny little question by comparison, but it actually is related. So let me make the leap. So I want to ask the question, what features of the universe are correlated with classicality? So I want to maybe consider classicality as a condition. We know the universe has classical behavior. We know that's not the most general case for physics, that it has classical behavior. I'm someone who believes it's quantum at the bottom, that's the foundation, and classicality emerges due to certain physics. It seems like maybe the arrow of time, maybe locality and other things can be attributed to our need for classicality. And I'm very interested in these kinds of questions in general, but I'm not going to be so broad. The rest of my talk, I'm going to be very narrow and explore the process of ion selection, I'll tell you what that is in a minute, in a toy model and relate it to the arrow of time in particular, just in the toy model. And ion selection, so I'm going to say it in words and then I'm going to demonstrate in pictures what it means. So ion selection is the preference of special Pointer states of a system due to interactions with the environment that it has. So the preference means the Pointer states are stable. It means things that are non-Pointer states tend to be destroyed, including coherent superpositions of Pointer states. And pure non-Pointer states, in general, can turn into mixtures. So you can go from pure state for the system to a density matrix where probabilities are assigned to the Pointer states. We don't need that. So I'm going to illustrate all of this. So instead of dwelling on the words, I'm going to illustrate all this with my toy model. And I'm going to consider, so in general, just comment that ion selection, this process is considered an important ingredient to the emergence of classicality. So let me tell you about the toy model. It's an offshoot of something called the Caldera-Leggett model, which has been around for decades and is the tool that's been used in some of the classic papers on decoherence and ion selection. We talk about a world that's a combination of a system and an environment. And here's what the Hamiltonian looks like. So the system is just going to be a simple harmonic oscillator, and this is self-Hamiltonian. The interaction term is going to have this form. It's going to be sensitive to the value of the position of the harmonic oscillator and interact in this way with the environment. And then, of course, there'll be a self-Hamiltonian for the environment. Now, and the important thing is that these are different. These are both Hermitian matrices in the environment, and they need to be non-commuting for this to be an interesting model. Coleman de Lucia modeled the environment as an infinite set of harmonic oscillators with different frequencies. They take this very fancy order of limits and other kinds of limits of the different timescales. And even though this is something that describes, in principle, a unitary evolution, they get into a place where they model this with an irreversible stochastic equation that is applicable under certain conditions. And then they demonstrate ion selection. They've written about it, and others like Paz and Zurek and Habib have written about it, and others have worked with this kind of picture. Now, what I have done is modeled E as a finite system, solve numerically for a full unitary evolution in all regimes, whether there's an arrow of time or not, and demonstrate ion selection under certain conditions, sort of mimicking what's already been done with Caldera-Leggett. And then also now, because I can evolve this anywhere, and for any phase of the evolution, I can also explore ion selection in equilibrium. And so I want to show, for better or worse, I've done certain things in different so-called movies. So bear with me, because these aren't real movies. They're other sets of. Let's see if movie A. Oops, what's happened? Movie A, okay. So I just want to introduce you to what I have by introducing you to the system, first of all, decoupled from the environment. And so I've turned off the interaction, and I'm going to show you, and this is also how I'm going to illustrate other things, so I want to get you used to. So first of all, the system, I call it a harmonic oscillator, but it's actually just a 30-state Hilbert space, which is built to approximate a harmonic oscillator very nicely, as it turns out. I plot the probability distribution as a function of position, and also the real imaginary parts to give you a feeling of the phase. And you can just see that it's just a wave packet going back and forth. And then you can see that the energy is constant. Here's some sort of features over time. Everything, the entropy is 0. And then I've gone to some way later time, and it's still just this packet oscillating back and forth. And so I just want to say it has nice stable behavior. It looks like a harmonic oscillator, even though it's a finite system. And that's really all I needed to say about that. And then now I want to introduce the Schrödinger cat. So I'm apparently not quite mastering the jiggling between slides here. So Schrödinger cat is just two wave packets coherently, and they just do what coherent superpositions of wave packets do. So that's the Schrödinger cat state. And then now I want to, we just showed movie B. Now I want to turn on the interaction. So I want to take a Schrödinger cat state and turn on the interaction. And, oh, that was sweet. How long has it been like that? Oh, I know what I have to do. Okay, it's being clever, more clever than me. So the thing is that once you have the interaction on, we can start in a product state where each subsystem is in a pure state. But the general, with the interaction, you'll get something more complicated, and you'll need to describe the harmonic oscillator by a density matrix, which could have a more general form. And so what I'm going to do is show you eigenstates and eigenvalues of the density matrix, and I'm just going to show you the two most probable ones. So that's what I'm going to show you next. So this is a Schrodinger cat state with a here we go. I'll help. Okay. So here's the Schrodinger cat state. So the first thing that happens is that you have a Schrodinger cat state in a product state. So the probability, so the first two eigenvalues are shown there, and there's only one non-zero eigenvalue. It's a product state, and this is what a density matrix looks like. So this is just a junk eigenstate. It's whatever the numerically it came up with, but it's the only real state of the system is this Schrodinger cat state. And after a little bit of time, there's more than one non-trivial eigenstate, but it's still Schrodinger cat-like. And then as time goes on, the interaction continues,